Sometimes things aren't quite what they seem. This car body looks like it's made from metal, but it's not. Actually, it's a composite material which is stronger than metal. Damien McTaggart designs sports cars, not with a computer, but with a saw, a rasp, and a lot of polystyrene foam. He cuts and shapes the foam into a full-scale model of a new car to be launched at this autumn's motor show. It's so secret, he won't show us the whole thing. He's limited only by his imagination and the demands of his managing director. The advantage of not using computer-aided design is that he can see the results of his work full-scale in 3 dimensions. The disadvantage is that every change has to be done physically and is hard to undo. This is the raw material which will make up the body of the car, sheets of glass fibre. At this stage, it's soft and pliable and can be cut into shapes using a template. The transformation from soft sheet to hard car body starts here. The workers lay the sheets into moulds and apply liquid resin, which combines with the glass fibre so that it can be pressed into the mould with a roller. It will begin to set hard in just 20 minutes, so they have to move fast. They build up the material in layers, glass fibre sheets and liquid resin. The moulds were made directly from the foam model originally designed by Damien. Making cars out of glass-reinforced resin reduces tooling costs in the factory. When they've laid up the glass fibre and resin, the workers bolt together the individual segments of the mould, and the car body begins to take shape. They will leave the moulds overnight to set. If you look closely at sheets of glass fibre, you can see the fibres entangled in a random fashion. This gives the material its high tensile strength. When the resin is added, it bonds the fibres, resulting in a strong composite material, combining the properties of the 2 components. When the workers remove the mould, the glass fibre body is revealed beneath, but it's far from finished. The body goes through to a finishing shop to be prepared for painting. Here they remove mould seams and other imperfections. Glass fibre is dangerous to work with, so the finishers wear masks to protect their lungs from the dust, and extractors remove the dust from the air. TVR make just 22 cars a week. They're all handmade with great attention to detail, so they don't come cheap. The prepared bodies are taken into sealed chambers for priming and painting. They get at least 9 coats. Special clothing and masks protect the workers from the poisonous fumes and particles. The body's important, but so's the rest. After all, what's a sports car without an engine? The finished car. It's strong, it's light, and it's fast. It owes a lot to fiberglass, but not all resistant materials are manufactured. Wood is a remarkable material. It's strong, it's workable, it can be cut, carved, shaped, and even better, it does grow on trees. But the wood we use and the way we use it is changing. In the past, quality furniture was made from hardwoods. Softwoods, such as pine and spruce, were considered unsuitable, but things have changed. Softwoods can now be processed to make MDF and HDF, that's medium density and high density fibreboard, an improved wood product suitable for furniture making. These logs are being debarked in the first stage of the process. Next, they're hacked into chips in a giant blender. The chips are graded and washed to remove impurities. Then they're blasted with steam and mixed with resin. Once they've been dried again, they're formed into a giant continuous fibre mat. This mat goes through a hot press, 260 degrees Celsius to be exact. The press squashes it into 1/40th of its original thickness. The result is a wood panel board of consistent quality. In other words, there are no knots or splinters. The cut sheets are cooled on a giant wheel before being packed. So what can they be used for? Here's the answer. The Slaters want a fitted bedroom, and Andrew Carter is a designer. His job is to measure the room and draw up a plan. Andrew sends the measurements back to the factory, where they're entered into the computer. Each customer's room is different, so each design has different problems. The Slaters have a sloping roof, so their wardrobe units will have to be specially adapted from standard sizes in order to fit. These measurements will be sent directly to the factory floor. This system is called customised automation. The Slaters' order arrives at the beginning of the production line. Here, standard sheets of MDF, HDF and chipboard are cut to the correct sizes for their order. Chipboard will be used for inner wardrobe divisions, whilst higher quality HDF will be used for the more visible door fronts. The powerful saws can cut several sheets at a time. A computer numerically controlled, or CNC, drilling machine automatically drills holes in the panels. It's crucial that these are drilled to the right depth and in the right places. A controller continuously checks for accuracy, using optical templates for position and a gauge for depth. An operator enters the Slaters' door measurements into a CNC routing machine. This machine produces the carved pattern on the wardrobe doors. This is where the properties of HDF are most obvious. It can be worked, finished, sanded and painted in the same way as good quality solid wood. The Slaters' routed door panels are spray painted in a sealed chamber, which protects the workforce from the noxious fumes. The finished panels are assembled into their individual orders, ready for quality control and dispatch. Efficient design and manufacturing control pays off when the Slaters' bedroom is fitted. Because everything fits together perfectly, their bedroom can be installed in just 5 hours. Metals make music, and different metals make different sounds. This is due to the different size and shape of the instruments, and to the resonance values of the metals themselves. To bend, coil and shape the instruments, manufacturers need to understand how metals behave. Musical instruments may not have changed much, but modern manufacturers modify designs using computer-aided design, or CAD. This allows them to produce exact specifications for the individual components so that everything fits together perfectly. Yellow brass, red brass, nickel silver, stainless steel. These are the raw materials of musical instrument manufacture, the input. In the workshop, these raw materials are customised. Pipes are cut into lengths and drawn on a bench, which adjusts length, thickness and diameter. Processing begins. Chain drawing quickly and easily adjusts pipe dimensions, but for more critical tolerances, a mandrel is inserted into the tube, which keeps it a constant width and diameter. Hydraulic oil is used for lubrication and cooling. This pipe will be the slider on a trombone. Have you ever wondered why brass instruments are coiled? Because otherwise, you'd never be able to reach the keys. But bending tubes is trickier than you think. First, they dimple them in a press, and then bend them in a vise. Then they blow out the crimp on a blowing press. This pumps hydraulic fluid into the pipe at great pressure. The result is a perfectly curved pipe. So why don't they just bend the pipes? A CNC drill is used to machine parts to very fine tolerances. In this case, part of a valve group. This is made of stainless steel because dissimilar metals slide more easily against each other. Why is this important for moving parts? Dennis uses a template to cut a sheet of red brass to make the bell for a trombone. Red brass is used for bell making because its high copper content gives good tonal quality. Once he's cut the sheets, he hammers them into a rough bell shape or breaks them in. Then he cuts teeth into the edges to make the seam, and he hammers these over, adding spelter, a mixture of brass, silver and flux, along the seam. Silver is used to help it flow. He uses a welding torch to fire the seam. The bell end is shaped on a CNC lathe. This quickly and accurately shapes the bell and cuts away any surplus metal. These bell ends are joined onto the rest of the bell and the seams hammered and finished. When the bells and pipes are made, they still have to be buffed and polished before assembly. Brass instruments need to look shiny. Everything must be polished, but some parts are too small to be done by hand. This is where everything finally comes together. Pipes, valves, slides and stops are all assembled into trumpets, trombones, horns and euphoniums. Precision is essential. The combination of poisonous solutions and electricity mean that care must be taken when electroplating. Many of the instruments are silver-plated, but first they're given a coat of copper, because silver bonds better to copper than it does to brass. Hugh's job is to check the instruments at the end of the line. Do they look right? And most important, do they sound right? He checks tonal values with a stroboscope and by ear. And once they're found to be perfect, the instruments are ready to perform.